Bismillah ar-Rahman ar-Rahim. So, chapter 1. The root of an equation. So this is the first chapter in our module Numerical Methods for Science and Engineering. If you have not seen the introduction, please see the first video where I introduce the module. In this chapter, we will see how to solve an equation. The root of an equation means to find the solution of an equation. So let's write it here, chapter 1. First page. We are I think 16 in September 23. So Saturday 16th September 16 September 23 in Malaysia. In Malaysia. In this chapter, we will see the problem, the method, an application through a concrete example with a pen and calculator, how we apply the method. Then we will see how to implement the method, an algorithm, and then we will discuss the pros and cons and what we call the edge cases analysis. And finally, we will give an overview on the other methods. So, other methods. I will subdivide this chapter in 6 sections. In this first lecture, we start with the problem. So first of all, we define rigorously the problem. So our problem is to solve a function f of x equals 0, find x in the interval AB. You are given an equation in this form, an expression, function of x equals 0, and you are asked to find the root of the equation, the solution of the equation in the interval AB. Or graphically, let's draw the axis, the x-axis and the y-axis. Between A and B, the curve this is the image of B, and this is the image of A. And our curve should be like this. It cuts. Yeah, there must be one single root between A and B. So this is the curve of F. This is the curve of F. This is FB, and this is FA. Where FA is the image of A, and FB is the image of B. And this is the root, XR star. R means the root and star means the exact. So XR star is the root of our equation. Okay. And there must be two conditions in order that root exists in this interval AB. So F must satisfy the following conditions. First of all, it must be continuous. F must be continuous. Continuous. And F must change its sign at the endpoints. If it is here negative, it must be here positive. And vice versa, if it was positive, it must be here negative. How we formulate that mathematically? We simply say Fa by Fb is negative. If they have the same sign, positive, positive, or negative, negative, it will be positive, not negative. So to say that Fa has a different sign of Fb, we write the product is negative. We don't have to perform the product actually. It's just a notation to say that Fa and Fb have different sign. So we can also write that Fa and Fb have not the same sign. Have not the same sign. These two conditions both must be satisfied. Let's see an example, several examples. So let's write x-axis, y-axis, and for examples where these two conditions are not satisfied. So first, we have our curve like this above the axis. This is A and this is B, and their images are both positive. So it's impossible the curve between A and B cuts the x-axis. Or like this, and the curve is below the x-axis. This is A, this is B. This is the image of A, and this is the image of B. Here also, we have no solution. Or, let's say, function change. This is A, this is B. Function change its sign. This is the image of A, this is the image of B, but is not continuous. There is a asymptote. There's an asymptote, a line asymptote that make the function discontinuous. So, albeit the function change its sign at the endpoints, there is no solution. There is no root between A and B because the function is discontinuous in AB, in the interval AB. A third example where the two conditions are fulfilled, are satisfied, but the curve. So there are A and B. The curve cuts the x-axis in several points, in actually an odd number of points, means 3, 5, etc. Here, three times. This will not work also because we have multiple roots, several roots between A and B. And we have said at the beginning that our interval must contain a single root. So we have actually three conditions. If there is a root, it must be single, unique. The function must be continuous, and it changes its sign. Otherwise, it's impossible to get a single root in this interval. So let's write here the case here, multiple roots. In this case, you have to reduce the interval to bracket one, to catch one root, one particular, this one or this one or this one. And you apply the method 3 times to obtain each root, if you are interested to find all the roots. So this is the problem. Now let's see the method. So chapter 1, second section, Abou Kamel's method. So the author is Abou Kamel. Abou Kamel al-Misri. Misri means the Egyptian. The Egyptian. Al-Misri. Or in Arabic, Abou Kamel al-Misri. In 1850, he was born in 1850 and died in 930, third Hijri. The first golden age of the Muslim civilization, Hijri century. The same period of another great name in mathematics in the Muslim and Arabic world was Khawarizm. But Khawarizm was in Baghdad and Abu Kamel in Egypt. They have never met each other, but they were almost in the same period. Abu Kamel has written several books and treatises. The most important book is the book of algebra, Kitab al-Jabr. And he has a treatise on this method. It was actually lost, but was preserved by other mathematicians and used for centuries in the Muslim world. So it's a well-known method, albeit the original treatise was lost. Some books also was lost, but we have several others. He has written, I think, maybe 10 publications. You can check, of course, Wikipedia on Abu Kamel al-Misri. We don't know much about his biography. Know his birth date and when he passed away, but we know him through his books and treatises. So, the method starts with a false point, and the original title of his treatise is Bayn al-Khata'ayn, between the two false points. So we start with the false point. How the method works. The false point. So let's draw the x-axis. This is the x-axis. This is the y-axis. This is A interval. This is B. We understand and analyze the method graphically. It's a graphical method. Its reasoning is based on geometry. So let's draw the curve. As we said, this is the true point. This is the root, the true point, the true point. This is the unknown, we don't know it. So what Abou Kamel has proposed is to join the images. So this is FB and FA. To join the images at the endpoints by a chord, by a line. And the intersection of this chord with the x-axis is the false point, is XR. Is the root, but it's not the root, is a false root. And here is the true root. This is the true point, and this is the false point. The true point, we don't know how to calculate it. If we knew the true point, we would not do all this, of course. But the false point is very, very easy to calculate. So let's write here XR is the false point. How to calculate it? So let's observe the two triangles here between the chord and the x-axis, and the other triangle here, also between the chord and the x-axis, and analyze them. So let's do that in another page. Okay. So how to find XR? How to find XR, false point. Let us repeat, but only the triangles. This is the chord of Abou Kamel. And let's call this XL and this XU. XL, this is the x-axis. XL means lower, the lower bound of the segment is equal to A. And XU, the upper bound of the segment is equal to B. We use XL, XU because later you will see the interval will change. And an interval is characterized by its endpoints, the lower bound and the upper bound. And their images FU and FL. So what we can see here, this angle is equal to this angle, and this angle is equal to this angle. This is a 90 degrees angle, same here. So we call that similar triangles. Call that when two triangles have exactly the same angles, the three angles are equal, we call them similar triangles. And when you have two similar triangles, there is a property, a well-known property that tells us if you divide one side from one triangle over the corresponding side of the other triangle, you obtain the same ratio, whatever the side you choose. So this one over this one equal this one over this one, and this one over this one equal the same ratio. So let's use this property here. We are interested to find this point. This is XR. What we'll do, XU minus XR, let's write it here, XU minus XR over XR minus XL, the length, XR minus XL, equal this side over this side. So this is FU, the image, and this is 0, the x-axis. So it's FU minus 0. And here we start with 0 minus FL to obtain a positive length over 0 minus FL, because FL is negative. So all the elements here are positive. They are lengths. And our known is XR. We have an equation, one single equation, and one single known, and it is a linear equation. It's very easy to solve. So what we will do, the unknown XR one side, and all what we know, we put it at the other side, at the right side. Now let's do that. It's very easy. XU minus XR minus FU over FL by XR minus XL. Let's draw here a line in the figure and the equation. So the unknown here is XR, and here is XR. So let's write it XR and its coefficients minus 1, and here it is minus FU over FL, but when we bring it to the other side, it becomes plus. So FU over FL. And we have here XU become minus XU plus minus by minus plus FU over FL by XL. And hence XR minus FL plus FU over FL equals minus FL by XU plus FU by XL over FL. We can then eliminate FL and we get the final result, XR equal FU XL minus FL XU over FU minus FL. Okay. This term is never equal 0 because FU and FL have different signs. So if this is negative, we get a positive number. If this is negative, we get a negative number, but never zero. And this is the formula of the false point method by Abou Kamel al-Hijri, by Abou Kamel al-Misri, by Abou Kamel al-Misri. You see here we have the images of the endpoints in the numerator and denominator. And in the numerator, we have only x. And we change the position. Here, fu minus fl. Well, here, xl minus xu. So it's very easy to remember and to apply. We just need the value at the endpoints. Yeah, that's the false point. But the false point, the first false point, is still not close enough to the true point. We need an iteration process. Let's write here iterations. Let's write here iterations. And let's draw the axis. Let's draw the axis here. This is the x-axis and this is the y-axis. This is A and this is B. And we have our curve should be like this. And this is the root, the true root we are looking for. So Abou Kamel methods, as we said, we draw the chord joining the images of the endpoints. We start with this interval, with the first interval, 1. First interval tells us that XL, the lower bound of the first interval, it's not power 1, it's the first interval, equal A. And the upper bound of the first interval equal B. First interval is defined by A and B, which are given. This is the first interval. And using the formula of Abou Kamel, the chord, we get XR1. This is XR1. We get, using Abou Kamel method, I will write AK, we get XR1. But as you can see here visually, it's not close, it's not that close. It's close, but it's not that close. It's still very far, actually, from the true solution, from XR star. So the method will not end here, actually. What we do, we take the image of XR. This is FR. This is the image of XR1. And we get a new interval that contains the root, the second interval. Now the endpoints of the interval are this one, B and XR1. And we repeat exactly the same process. We join the images of the endpoints of our new interval. And we cut the x-axis here. And we get the second point, XR2. So this is the first chord, and this one is the second chord. So second interval XL of the second interval is not A, is XL1. This is the second interval. But the upper bound is B, stays the same. And we get, using Abou-Kamel method, XL2. And the same, the image, because we join the images are always carried by the curve of F. This is the curve of F. This is the curve of F. So we get the image, and we repeat the same process. To get XR3. And then we repeat also again to get X4, and so on, till we are close enough to the root. So it is an iterative process. At each iteration, we build a chord, we get the intersection of the chord with the x-axis, and then we get another interval, a second interval, a third interval, a fourth interval. So this is the third interval. This is the third interval. And then the fourth interval, and then fifth, and so on. And we start, of course, with a given interval. We shrink this interval until the solution is not exactly the same, but is very close to the exact root. So this is the idea of iteration. Let's write it here. XR, the sequence, XRI, I from 1 till n, the given number of iteration, tends to XR star. I say X in French, normally we say X, XR star. Now there is a problem when we choose the next interval. We start with this interval. We see that the next interval must contain the solution. Actually, when you get XR, first XR, you have two intervals at the right and at the left. You have at the right, at the left, this interval, and at the right, this interval. But this interval contains nothing. It doesn't contain the root. So we are not interested in using it. We choose the right interval, and we continue choosing the right interval until we are close to the solution. Because here we see the figure, we can observe the figure, we can decide which interval, left or right. But when we work with a pen and calculator, we generally don't have the figure. So we need a simple rule, easy to use, in order to know which next interval we have to choose, at the left or at the right of XR star, And we repeat this rule for each XR along the iteration. So the title will be here, the choice of the next interval. How do we do that? Choice choice of the next interval. We have three cases, actually two cases. The third is a theoretical case. So let's see the two cases. Subdivide our figure here. Compare the two cases. Case number 1 and case number 2. and let's try just to draw, the two axes. And the y-axis, and choose XL, XL, and XU at the ith iteration. At the ith iteration. Same here. XL at the ith iteration, XU at the ith iteration. So we are at a given interval, the first, the second, anyone. And in this interval, we have the image. We have also here the image. So the curve here will be like this. And our solution is this point, the true solution. Our chord will be like this. It joins FL at the ith iteration and FU at the ith iteration. And we get the point XR at the ith iteration. And here it's its image. FR I. So this is the interval number I, interval number I, or the ith interval. What we can see here, now this is XR, it subdivide the interval XL, XU. XL is not clear here. XL and the ith. So it subdivide our interval XL, XU into parts. The left, there is only left or right, there is no other case. So at the left and at the right. And we can see that the solution is at the left, not at the right. So the next interval must be this one, because it contains the root, not this one. And we can see that to be at the left, the chord, not the chord, the arc of the curve. This is the curve of F. The arc of the curve must cut at the left, which is also, which can be also expressed as the sine of FL and the sine of FR, not FU. FR is different. It was positive, and because it cuts the axis, it becomes here negative. So all the images are carried by the curve. So it starts positive, and then it becomes negative. And we said, of course, that our function is continuous in the original interval, so it is continuous in any subsequent interval. So the rule is very simple. FL I by FR I is negative to get the left left side. And be careful here, FR, not FU. We are comparing FL and F. Here, FU doesn't play any role. We could, of course, reason with FU and FR. It's also possible. But here I prefer to use the left and the R position. So XL has an image, FL, and XR has an image. We use the images at the left and at the root, at the false root, the false point. So FLI by FRI is negative. We are at the left. Now let's see the other case, where it's not at the left. The curvature change and become like this. This is the root, the true point. And let's draw chord. So let's write here FLI, FUI, and this is XR, the Abou Kamel point. Let's call it the Abou Kamel point or the false point, the proximate point, proximative to the true solution. And its image is here. This is FRI. So we can observe that that part of the curve, the arc here of the curve, does not cross the x-axis. And as before, XR subdivide the interval XL, XU into parts, the left and the right. But this time, it is the right interval, subinterval, that contains the solution. So we choose the right here. And you can see that the sign at the left, FL and FR, have the same sign, are both positive. They could also be both negative if we draw the other case. It's the same case, but I mean, if both points are above the x-axis or below the x-axis, it's impossible to get the solution in the left interval. So the only possibility is the other interval at the right. So here the rule also is very simple. So this is the interval I, ith interval, and the rule is also very simple. FLI, I also here consider FL and FR, not FU. FU will not play any role here. So by FRI, if it is positive, means if they both have the same sign, it is at the right. The third case is when FR equals 0. That is, when you multiply, you get 0. You have a product, it's either negative, positive, or equals 0. But equals 0 means FR equals 0, because FR is not 0, impossible. If it was equals 0, it was the solution. And if R equals 0, we stop. There is no next interval. This is the solution. So there are only two cases to catch the next interval. See the sign of FL and FR. And actually, you don't have to perform the product. You just compare the sign. If FL has a different sign of FR, it's at the left. This chord this arc, this part of the curve, this arc of the curve has crossed the x-axis. That's what it means that FL and FR have different signs. And if they have both the same sign, it's impossible that this arc cuts the x-axis. So it is at the right. So it's very easy to understand and to remember. Well, that's it for the choice of the next interval. Just at each iteration, we just have to compare the signs. Let's here observe something before to go to the next point. If FRI is negative, it is at the left. Otherwise, it is at the right. This is the rule. But what does it mean at the left, at the right? So how to choose how to write that formula, the next interval. So let's say here at the left means that XL of the next interval equal and XU of the next interval equal XL, XU. If we know XL, XU, we know the next interval. And at the right, XL I plus 1 equal and XU I plus 1 equal. So at the left, when I imagine we have here the x-axis. This is the interval at the ith iteration. At the left, it becomes like that. The only bound that change, the end point that change, is this one. It becomes the upper. The XU, the upper bound, will change, but the lower bound will not. So the lower bound will stay equal to the previous interval, but the upper becomes the XR, the new XR we find in the previous interval, XRI. That's what changed. While here again, this is the interval. Let's say this is XR. If we take at the next iteration the right interval, that is this one, the upper bound will not change, but the lower bound will. So the upper bound will not change because it stays equal to the previous bound, and this one becomes XR I of the previous iteration. So only one endpoint will change. At the left, it is the upper bound. At the right, it is the lower bound. That's the rule for the next interval. Now another question important when you have an iteration. When we stop this iteration, what is the break condition that stops, that break the loop of iterations? When we stop, of course, in this case, when XR is close to XR star. XRI at the ith iteration is close to the XR star. So the break condition, write it here, another subsection, the break condition. This is actually the last subsection of of the method, the section method. Section, we are talking about Abou Kamel method. We started by the false point, then the iteration, then the next interval, and now we are in the break condition. How we stop the iteration. So we stop. There is actually two conditions. So let's say the first. Let's study the first. We need that XR I at the ith iteration minus XR star becomes very small. That's what we need. But we need to quantify that. We need a formula, not a sentence. Because we need to use a pen and calculator when we apply this method. And also in implementing this method, we need to write an algorithm. And an algorithm doesn't work with sentences. We need to quantify that. So there is two types of error. The absolute, this is an error. The distance between the false and the true point is called an error. So there is two types to define an error. The absolute error is what we just have written. So small e at the ith iteration is by definition xri minus xr star, the false point minus the true point. It can be positive or negative. So, and the relative error is defined by big E at the ith iteration is noted by big E. Big means relative, small means absolute. Relative means it's also the error minus XL star, it's the absolute error divided relative to the current false position or false point. So it's the current value of XR minus the exact value over the current value. And in general, we multiply also by 100%. It is a percentage of the current value. It is relative to the current value with a given percentage. So this is the definition. Let's see this the difference the difference between these two types of error through an example. Let's see an example. There, let's put them side to side. Let's write here, suppose we know the exact solution of one equation, particular equation. We find that solution is 1500, for example. And we applied the Abou Kamel method. At the fifth iteration, we found XR5 equal 1510. So according to the definition, we have E5 equal 510, 1510, 1510 minus 1500. And we get equal 10. So is it a small error? Because we are interested to find a small error, of course. We said any numerical method has an error. But of course, we are interested to find the smallest possible. So is this number, a small error, or a large one? Let's see another example. It's small, of course, we can see it's small. No, not of course. You will see. So let's take another example. where the data here is different. The magnitude of the data is different. So we have here 0, 0, 25, for example. We know the solution of this new equation is 0, 0, 0, 25. And after 3 iterations, for example, we have found the number 0, 0, 3, 17. And we do the same, the error, using the definition, the absolute error. So it is the current minus the exact. So 0, 0, 3, 17 minus 0, 0, 25. We obtain equal 0, 0, 2, 9, 2. Is this a small number or a large number? Is this a small error or a large error? So we cannot conclude actually. It depends on the magnitude of the data. So small or large is relative to the data we manipulate. Here we manipulate, we are using small numbers. So we expect an error to be smaller than these numbers. And here we manipulate large numbers, and we expect also the error to be small compared to the data. So we need actually, the absolute error is not a good choice here. We need to use the relative error. So if we apply the rule, the definition of the relative error, we find here in the first example that it is 10, the absolute error, over the current. And we find equal 0 by 100%. And it is equal to 0.66%. That means the error is 0.66% of the current value. It's very small. It's very small compared to the given data, the input. And here, E3 is 0.029.2 over the current value, 0.0370 by 100%. And we find it is equal to 92%. 92 is large. So it is very large error. It's very large compared to the data because the data are already small. So you compare a small thing to a smaller. So 92% of the input data of the current XR. So it's really very large. So when we stop the iteration, we will use actually the relative error, not the absolute error. But as you see, there is a problem here. There is a problem. The XR star is a known. Don't know XR star. So we cannot apply this rule directly. We use as a break condition a slightly different formula. I'll show you that now. My notes. So, because XR star is a known, we use the current, the following relative error. It is a relative error, but slightly different. We compare actually the current value of the false point with the previous value of the false point. Let's write it. It is an approximative error. EA. A means proximative. Proximative error is not the true error. E, big E, is an approximative error, relative error. And by definition, it is equal to XRI minus XRI minus 1, the previous. Not power, of course, it's the previous XR over XRI, the current. So the current value of the force point minus its previous over its current by 100%. Because if you see, this is the error we will use. Let's suppose this is XR star, the unknown. And we started XR1 here. Then we get XR2 here. Then XR3 here. And then XR4, and then XR5, and then XR, and so on. So this point, the distance between this point shrinks, tends to 0 when we are close to the solution. So this error doesn't tell us the distance, how close we are to the exact solution. It doesn't tell us because we don't know XR star. But it tells us how close the points, the false points, are to each other. When they become really too close, we have to stop the iteration because the next XR, the next false point, is almost the same of the current point. There is no progress in XR. So when the proximative error reach a given value, we have to stop. That's the meaning of this error. It's based on the fact that the false point tends to be very close to each other in the vicinity, in the neighborhood of the exact solution. And you can also observe another important thing, that this is, of course, at the ith iteration. The ith iteration. And this is the previous. Let us observe that here at the first iteration, because there is no previous iteration before the first iteration, for the first, we just started. For the first chord, there is no previous chord. So the first iteration will be 100%. That means we have to do at least 2 iterations. And at the second iteration, we must check whether the value, or the absolute value of EAI is smaller than a given bound. If it is smaller, for example, to 1%, we stop the iterations. So this is the break condition. This is the main break condition. There is another break condition. This is also by definition. That's right, yeah, the second break condition. We know, let's draw again, but quickly. This is the root. And let's say the interval, and let's say this is the images, not the XR. They're images. Let's say this is FR1. The images are carried by the curve of F. This is FR1, and then FR2, and then FR3, and so on. They go to the intersection, to the x-axis. They go to 0. They are here negative, and they decrease in absolute value. Their absolute value decreases until they are close to 0. They could also be carried by this part of the curve, depending of the example we choose. So the second condition is based on the absolute value of FR. If the absolute value of FR at the ith iteration becomes close to 0, we stop. We stop. Here we don't need a relative error. This is actually an absolute error. It's the distance between FR at the ith iteration and 0. We don't need, because we manipulate 0, you don't have to divide by 0. So when FR is sufficiently small, we can also consider this as a break condition. So this is the second break condition. So that's it for the second section, the method, Abou Kamel methods, Abou Kamel's method. Let's now go to the third section to apply this technique with a concrete example. And we need a pen, of course, and a calculator.